students. So I'm very pleased to welcome Dr. MaryAnnPart1. She is the program manager of the Department of Energy Computational Science Fellowship. And that's why I was encouraged. I met MaryAnn at a SciTech Department of Energy conference, in a workshop conference. And that's why I always say to students, I always try to meet at least 5 people when you go to conferences, because if I didn't do that, I could have missed a chance to meet you. So I'm very glad that you're here. Thank you for coming.
Okay, thank you very much. Thank you for the opportunity to be here. I'm very happy to be here to talk to you about the Department of Energy Computational Science Graduate Fellowship Program, which we call DOE CSTF, because it's too much to say that whole thing. So anyways, I'm happy to be here. And so before I get started, I just would like to kind of get an understanding of who is here. So how many people are faculty? Okay, great. And so is students? Okay, good. And how many are graduate students? Okay, okay. Any undergraduates? Okay, great, good. All right. Well, what I'm going to do is, first I'm going to talk a little bit about why HPC, so why high performance computing, and then I'm going to talk about the program and its benefits and how it's very unique and different from other programs that are out there. So please feel free to stop me during the talk if you have any questions. I'm happy to just go as we take the questions as we go. So why HPC? Why high performance computing? I'm sure everyone out here has some knowledge about high performance computing. Probably, maybe you heard about it in 2002 when the Japanese introduced the Earth simulator and overtook the United States in the first place position in terms of the most powerful computer. Or maybe you heard about in 2006 when Oak Ridge National Laboratory introduced their supercomputer that they call Jaguar, which was the first to go into the teraflop scale. Or maybe you've heard recently this year that Roadrunner over at Los Alamos National Lab, which is not so far away from here, was introduced, and that broke the petaflop scale. Or maybe you're interested in some applications. I know a lot of people here are computing at Lone Star at TAC. This application I think is really fascinating. There was an application that was running on the TAC supercomputer, which was done in real time for canine laser surgery, which was being conducted in Houston. So real time, they had laser surgery going on, and the real time data was, transferred over to TAC, which was, there was a lot of these programs running on the supercomputer trying to figure out the optimum temporal and spatial conditions for the surgery. So this was real-time cancer surgery, which I think is really fascinating to imagine that these are the kinds of applications which are being developed now in high-performance computing. But actually, what I'm going to do is not talk about those kinds of applications, but instead I'm going to introduce HPC in the context of my own personal kind of journey through HPC. I actually was a fellow in the DOE CSGN program, so I'm an alumna. And I'm going to talk a little bit about my own pathway to the PhD, how I overcame what I call the activation barrier, because I didn't know anything about high-performance computing when I started my PhD, but I had to learn a lot about it. How did I do that? And then also a little bit about how that impacted my research. So I was lucky when I was at University of Washington, which is where I got my PhD, to get involved in a program called Re-envisioning the PhD, which was all about examining the process of getting a PhD and looking at whether there was some improvements that needed to be made. And one of the things they did was they asked graduate students to draw pictures of what it was like to be on this pathway to a PhD. So a lot of the students drew pictures like this. Oh my God, it's this huge maze. I have no idea how to get through it. There's, who knows what I have to actually do to actually finally become a doctor. Some students describe their pathway as kind of somewhere going off the deep end. Who knows where it's really going to lead me to. And other students talked about their pathways as being something that was a feat of amazing, strength that you had to go through to overcome that. Climbing great bridges, crossing things. In chemistry, we think a lot about reaction coordinates, which describe what has to happen in order for a chemical reaction to happen. So on an energy scale, you talk about being in a reactant state and then having to overcome some kind of energy of activation in order to get to a product state, which is a lower energy state. So for many of us, the product state in terms of the PhD pathway could be a variety of things. It might be discovering new knowledge, being that one person to know something for the first time and to let the whole world know about it. It might be actually having gainful, steady employment after all those years of school. It also could be prestige or the reward of knowing that you're doing terribly exciting, intellectually challenging work. So for myself, my starting state, my reactant state, was that I had an interest in high-performance computing. I actually worked in the computer industry for about 16 years before I went back to school to get my PhD. So I had some computer background, but I didn't have any experience with high-performance computing. But I was really interested in HPC. I was kind of excited about the idea of being able to compute on some of the supercomputers. And I also did not have any help in my immediate sphere. You're lucky here because Dr. Velasquez has created this computational science program, and there's a lot of faculty members involved in it who are all familiar and are here to support you. In my own area, there were people who were doing computing, but not high-performance computing. So some of the key things that I did, or that helped me to overcome my activation barrier of learning about high-performance computing are listed here. There's something called ACTS, which is the Advanced Computational Software Toolkit, which is funded by the Department of Energy. And I went to a workshop and utilized that tool. Then I did a practicum. So part of this fellowship program is doing a practicum. You go to one of the DOE labs and you work for a summer. And then I got a grant for supercomputer time at Lawrence Berkeley National Lab. And I also got involved in a scaling reimbursement program, which gave me a ton of supercomputer hours. So the ACTS toolkit is just what it is. It's a toolkit of software applications, packages that are available that run on the supercomputer for numerical analysis, code development. There's development libraries. It's just a whole plethora of tools. So since I came from a domains area of chemistry, I didn't really want to spend my time kind of reinventing the wheels or inventing things that were outside of my discipline. So I used some tools which were already designed to run on the parallel supercomputer to do some of my basic numerical linear algebra. And then I was applied for a grant, and through the program we're now setting up procedures to help fellows that are in the program to get grants working on the supercomputers in the DOE labs. Over here I show you the amount of the allocation awards that I got over the years that I used. And here I just have a summary of the usage of my computing hours. So of course I started out really small, just getting things going. My codes I developed initially in order to prove that the numerical algorithms that I wanted to use to solve my problem worked on my problem. I coded it up in Mathematica and ran it on a workstation, and then I converted it into C code again on my workstation, and then I developed the code using these libraries on the supercomputer. So the scaling reimbursement program was really important because you might notice here that the hours that I used and the hours that I would charge exceed by quite a lot the hours that I was allocated in that grant. Now normally they won't let you just use more hours, but I was in a scaling reimbursement program which allowed me to get reimbursed for any hours that were run on large jobs, basically using 64 or more nodes, basically were free hours. So they were trying to, the whole program was designed to try to help people scale their codes to large scale. So anytime you used a lot of processors, you got the hours for free, which was really important. So next I'm going to talk about how HPC impacted my research. And so to do that, I'm going to have to give you a little background about my specific research area. And that was my thesis title, is the computational studies of macroscopic superposition states in the gaseous atomic Bose-Einstein condensate in multiple wells. Mouthful, right? When you do a PhD, you learn more and more about less and less, right? So very, very specialized field, but it's basically what I was doing was computational quantum mechanics. So hopefully you took a bit of physics so you know what that means. And the system I was studying is called the Bose-Einstein condensate. Are there any physicists? I know you're a physicist, so maybe you've heard of this. Anyways, it's something that was predicted by Bose and Einstein in 1924. It took about 70 years for anyone to ever realize it in the laboratory, but someone did. And as a matter of fact, these three researchers who discovered it in the lab actually created a Bose-Einstein condensate, won the Nobel Prize for their work. So this is considered significant, very interesting area of research. And what it actually is what happens is that there are atoms in the Bose-Einstein condensate that normally when you think about cooling atoms, you go from a gaseous state down to liquid into a solid. But in Bose-Einstein condensation, it's a different kind of phase transition. These are just phase transitions, right? And what happens when the gases are very, very cold, nanokelvin cold, and very dilute, they go into a different kind of phase transition, which is called Bose-Einstein condensation. And why it's interesting is because what happens, there's millions of atoms in this Bose-Einstein condensation, and they're gaseous, so they're not bonded together, but they all go into the same quantum state, and so they behave like a single macroscopic quantum object. So just like in a laser light, right, all the photons are in the same quantum state. We know that because they're emitting the same color light, right? Well, it's the same thing that happens here, except it's atoms, and these are alkali atoms, like cesium or barium. So it's atoms. So it's kind of like an atomic version of laser light. So there's lots of people got very excited about this when this was first actually created in the lab, and there's lots and lots of interesting things that people have tried to do with it and are doing with the systems experimentally. And of course, it's a wonderful test bed for basics of quantum mechanics. And in my particular case, the kinds of things that I was looking at are the creation of these Schrodinger cat states. How many have ever heard of a Schrodinger cat? So it's this weird, crazy thought experiment that came up by Schrodinger, which to illustrate the strangeness of quantum mechanics. And it kind of comes out of the mathematical formalism, right? There's superposition states. But actually, these superposition states have been realized in the laboratory in a variety of different systems. And so we were looking at, there are people doing experiments, and we were doing in my computational and theoretical work, trying to understand whether or not we could make one of these macroscopic superposition states with the Bose-Einstein concept. So that's the kind of simulations that I was working on. And why would anyone care about this? Who cares whether you can make some crazy big giant cat? Well, the reason why the application that we were looking at was for quantum computing, which probably you've heard about. Quantum computers are a new kind of computer that has been positive. Actually, people have claimed to create a quantum computer. There's a company in Canada which is actually selling timeshare time on their quantum computer. And the interesting thing about quantum computers, because of the fundamental properties of quantum mechanics, is that they're much more they potentially are much more powerful than a regular computer. So a regular computer has a bit, right? It's either on or off. Well, in quantum computing, because of this crazy idea of superposition, the bit can be both on and off at the same time. So therefore, you can get exponentially more processing power out of a quantum computer for certain types of applications. So that's kind of the catch about it. Only you have to build a process in a certain kind of way to take advantage of a quantum computer. But there are quantum algorithms which solve the problem of factoring very large numbers, which probably some of you know is the basis for many of our security systems. So there's a very big interest in this area of information, both from a security standpoint and then also in terms of processing capabilities. And we're a very long way from actually seeing little cats running around in our laptops, but it's a burgeoning area of research. So what did HPC do for me in terms of my thesis? Well, what it did was it allowed me to use a novel approach to trying to address this problem. So I developed this code, so ran them on the supercomputer, went up to like 4,000 nodes that I was using, 4,000 processors, and nobody else in the world was able to use a supercomputer to try to simulate and analyze the system. So the most people were doing around the country was working on clusters, and most people were actually just doing work on their own little, individual workstations. So, and because I had so much computing power, I was able to use much more rigorous techniques. So of course we all know in applied mathematics you have to make a lot of approximation techniques and when you're going down to try to describe your systems, and I was able to use more rigorous approaches, and then also of course I was able to investigate much larger systems. And the system I developed on my PC, which at the time was a really souped up PC, the systems I could simulate, the largest was 16 particles that were trapped into 4 different wells. And when I converted it to my C code working on my workstation, I could get up to maybe about 32 particles. Well, and when I went to the supercomputer, I got up to 256 particles. And I was also investigating not only 4 wells, but 8 wells. So I just had a lot more capability to my system in terms of what I could do and what I could investigate. So in terms of how to solve the problem, this is in quantum mechanics, you know, the equation you work with is the Schrodinger equation. So here's a discretized version. It's just an ordinary differential equation. And so the computational challenge becomes a matrix vector multiplication problem. And the scaling issues for my problem are defined by this equation over here, which just defines the dimensions of the matrix and the vector. And the dimensions are scaled in terms of the number of particles in the system I'm simulating and the number of wells that the particles are trapped in. And you can see it's factorial, so it grows really big, really fast. Here's a table showing for 16 particles, the dimensions of my matrix was almost 1,000. You get up to 512, and we're talking about 22 million. So that's a pretty large matrix to work with. And it's not something you could ever try to solve on your workstation, even on a small cluster. And as it turns out, I was simulating systems with a variety of configurations. So here's an example of 52 particles in 3 wells. Here's 4 wells, here's 5 wells, here's 6 wells. And you can see the matrix structure there's a few things you notice. It's very sparse. It's not exactly tridiagonal, so it kind of has this weird pattern, but it's a repeating pattern. And it gets more complex as you go into more wells. So this pattern is more complex than this pattern here. And as it turns out, the computationally intensive portion of this problem isn't actually solving that ODE. It's figuring out where these matrix elements are. So these matrix elements correspond to some physical part of the system I'm simulating, right? So there's an algorithm that tells me where these entries are and what the values are. So that actually turned out to be the computationally intensive part of this particular problem. And I wanted to write my code so it was generalized in the sense that I could work with any number of particles and wells. And so when I first started working on this problem, I started working on this system of 128 particles in 4 wells, and it was, almost 400,000 squared was the size of the matrix. And I did a rough estimate based on just trying to run some estimates on trying to solve this problem on the computer, and then based on that, I estimated it would take 33 days for my algorithm to actually calculate where all these matrices elements are. And in the lifetime of a graduate student, that's much too long, since there was several different systems I needed to look at. So I looked at how to try to optimize this. And I just want to show you here that it looks like this is nice and simple and tridiagonal, but actually there's this fine structure inside of this matrix. So it's not as simple as just trying to figure out a tridiagonal matrix. So the first thing I did was a very, very simple brute force attempt at looking at this, and I just parallelized the process of trying to calculate these matrix elements. And it's just an embarrassingly parallel system. I just said, okay, if I was using preprocessors, I took a third of it and I ran it off on one machine and so on and so forth. Doing that, however, I was able to get it down from 33 days to 33 minutes, which is great, right? That's a big improvement in time. But it was still pretty much a rough, kind of a brute force way to do that. So then I did a few other things. For instance, you can see that this is basically kind of triangular in nature, so I figured out how to calculate the maximum width of the structure, and then I would just look for matrix elements inside the middle area here. So why should I even try to bother to look for a matrix element out here, because I know there's not going to be anything out there, but I could calculate the maximum width, so I figured out a way to calculate that. And then I did several other tricks in terms, they're kind of computer tricks, you know, in terms of optimizing the amount of memory I'm using, the amount of file I/O that I do, and so on and so forth. And based on all those optimizations, I was actually able to get the same problem down to 53 seconds. So I went from 33 days to 33 minutes to 53 seconds. So that was pretty good. I was pretty happy when I finally got the code down to this level. And then I could go off and start computing and start doing my science and figuring out what could we actually create these Schrodinger cats or not. Just to show you that my code actually really is pretty efficient, I have some speed up curves here to show you based on the number of processors. It's a log plot, you know, and how much time it took, and you can see that for this particular system here, this is we're looking at 512 particles in 4 wells. I'm really nice linear speed up, and then of course I hit a saturation point where adding more processors just no longer gives me additional speed up. And then for this system here, for 24 particles in 8 wells, I was able to get all the way up to over 4,000 processors and still getting really nice linear speed up. So this problem I could have kept going on. So what did that do in terms of my thesis? Well, first of all, I published my scaling work that I did. So I did basically a scaling study of my codes, and I optimized my code so that I could run them up to thousands of processors. And I published that work. I got a paper out of it, and that paper, of course, turned into one of my thesis chapters. Another thing that happened was that, you know, in solving this problem, in my rush to try to get to the science, I really did take a brute force to try to figure out how to solve this problem. You know, I just kind of used this algorithm and optimized it, whatnot. But along the way, I actually discovered or got some insight to some kind of more interesting ways to try to solve this problem, kind of more cool problems to work on in terms of just algorithmically how to solve this problem in relationship to the physical problem that I was doing. Had I had a little more time, I would have worked on that, but I didn't, so I pushed forward to the science. And I was able to investigate systems as big as 512 particles in 4 wells and 24 particles in 8 wells, and I did prove that we were, according to my codes in my simulations, you could create these Schrodinger cat states in these systems, which was pretty great. It was pretty exciting and really, really nice that we were able to show that you could do that. However, along the way, I also discovered something else, which is interesting. I'm not going to bore you by going through all the details of the physics of this, but we actually discovered a different kind of quantum state. So with this particular state, we expected to see this certain kind of Schrodinger cat, but we actually found a different kind of Schrodinger cat, which we now call the Siamese cat. And so I'm in the process of writing that work up and publishing that as well. So not only did I kind of prove my initial kind of hypothesis, but we also discovered something else, something new. Which again, we would be, if I had not been through the supercomputer, I would have never even seen these kinds of structures, because I did a study to show that these structures come about based on the number of particles, and I had to be able to go up to a larger number of particles. So in the end, how did HPC impact my research? I started out in a particular place. I got experience writing and winning grants, which of course is extremely important. Probably no matter what you do, as long as you continue research, you're going to, even if you're in academia, it's absolutely essential. If you go to a DOE lab, you have to write grants as well. But if you go to industry, maybe you won't have to write so many grants, but you're going to probably have to be able to sell people in your company about your ideas, and that's the same kind of thing. I was able to use a novel approach to my problem, so no one else out there was able to do the kind of work that I did in terms of investigating the system. And I scaled my codes up to thousands of processors. And I was available, because of that, I was able to investigate much larger systems than anyone else could even come close to. And then I encountered some cool problems to think about. Again, now one thing that's really important, and the faculty know this, is that always being able to come up with research ideas, what kind of things to investigate, and new approaches to solve problems. That's really important. So by going through this process, you discover more ways to approach problems interesting and have cool problems to work out. And then ultimately it led to some scientific discovery. Okay, so that's kind of my story about my own process and why HPC was important for my work. Next I'm going to talk about the program and its benefits, the requirements, and in particular I hope that I leave you with the idea about how this program is very, very different from the other fellowship programs that are out there. And we'll look at some of our fellows and our alumni, and then I'll try to talk about applying to the program. And like I said, anytime I'm open to discussion about this. So the program is funded by the Department of Energy. I actually work for a company called the Krell Institute. We're a nonprofit company, and what we do is we run this program and a couple other programs for the Department of Energy. And the Department of Energy funds, of course, both basic and applied research in science and engineering. And a lot of their work is funded, or you see that happens through the research at the DOE labs. So that's places like, I'm sure you probably know about Sandia National Lab, which is not so far from here. There's Los Alamos National Lab, there's Lawrence Berkeley National Lab, there's lots of national labs across the country. And high performance computing is one of a major initiative that the DOE is promoting through their DOE labs. And a lot of people think that the DOE funds only energy related because it's in their name, right, energy, but actually the DOE funds a lot of basic science. So that goes from, that biology, chemistry, physics, a lot of different material science, a lot of basic science that's being funded for the DOE. For the DOE CSGF program, we are supporting, this is just a sampling of the fields of students where we've supported. So I like to say it's, from aeronautics to zoology because it's A to Z, but really we support students across a variety of disciplines. And the common thread is computation, so everyone's doing computing. The goals of the program are basically to, from the DOE's perspective, they want to ensure that there's an adequate supply of trained scientists and engineers who can take advantage of high-performance computing. And they want to strengthen the ties between the DOE and the academic environment. So what work we're doing is also trying to foster collaborations between the advisors and the lab people, as well as the graduate students. And then raising visibility of the careers in computational science. So that's another thing that we do through our program is that we don't probably find in other fellowship programs is kind of career and professional development and even helping people to figure out where to try to get jobs. And for our program objectives, we're basically really trying to find doctoral students that are doing novel work in computational science and engineering in this broad area. So you could be sitting in a math department, a computer science department, or in engineering or whatever. And we're trying to encourage the next generation of HPC leaders. So we're not just trying to fund PhD students, we're trying to actually develop the next generation of leaders in the field. And we provide financial and other support to talented students who are studying in CSE and want to complete their practical work in the DOE lab.